In this video, I'm going to explain the solutions of exercise 9.5 NCERT Class 12 Maths. But before that, I would like to give you an overview of the method. So the equation which can be written as dy upon dx is equal to some function of y upon x, or dx upon dy as some function of x upon y, is called a homogeneous differential equation. And the method to solve this kind of differential equation is, in this step 1, first we rewrite the differential equation in this form or in this form, and then if the differential equation is in this form, we assume y is equal to ux, let it be equation number 1. Then we differentiate it with respect to x, dy over dx is equal to u plus x du upon dx, and let it be equation number 2. Then we replace dy upon dx by this expression with the help of equation number 2, and we replace y upon x by u, because from equation number 1 u is equal to y upon x, so we get an equation of the form u plus x du upon dx is equal to fu. Then we transpose this term to right hand side. We get x du upon dx is equal to fu minus u. Then we transpose the whole expression on the right hand side in terms of u to left hand side, and x upon dx to right hand side. We get 1 upon fu minus u du is equal to 1 upon x dx. And as you see, this is variable separable form, so we integrate both sides and we proceed from this step as we have done in the case of variable separable differential equations. And afterwards we need to replace u by y upon x, since according to our assumption y is equal to ux, that is u is equal to y upon x. So this is overview of this method. Now we are going to start exercise 9.5. Now exercise 9.5 NCERT class 12. So the identification of a homogeneous differential equation is degree of all the terms are equal. So as you see, degree of this term is 2, degree of this term is 2, degree of this term is 2, degree of this term is 2. So this is quite easy to identify a homogeneous differential equation. And once you identify that the given differential equation is a homogeneous differential equation, you need to write this in the form as dy upon dx is a function of x and y. So first we have to transpose dx to left hand side towards dy and x square plus xy to right hand side towards x square plus y square. So we may write it as dy upon dx is equal to x square plus y square upon x square plus xy. Let it be equation number 1. Then in the next step we assume y is equal to ux. Let it be equation number 2. Now differentiating equation number 2 with respect to x, we get dy upon dx is equal to, you need to apply product rule over here. So by product rule, if we differentiate the product of u and x, where u is a function of x and y, u differential of x is 1 plus x differential of u with respect to x du upon dx. So dy upon dx is equal to u plus x du upon dx. Let it be equation number 3. So we have to replace dy upon dx by u plus x du upon dx over here on the left hand side of equation number 1, and we have to replace y by ux on the right hand side of the same. So here if we write this expression, we get u plus x du upon dx is equal to, on the right hand side, x square as it is, plus if we replace y by ux, it becomes u square x square divided by, here in denominator we have x square plus x as it is, and we have to replace y by ux again. Here we have ux. So we have here in the numerator x square plus u square x square divided by, in denominator we have x square plus x into ux square. Now proceeding from this step, we have on the left hand side u plus x du upon dx is equal to, in the numerator we take x square common, we have 1 plus u square in the bracket divided by, in denominator we take x square common, we have 1 plus u in the bracket. Now here x square is cancelled by x square and we have u plus x du upon dx is equal to 1 plus u square upon 1 plus u. Now transposing u to right hand side, we have on the left hand side x du upon dx is equal to 1 plus u square upon 1 plus u minus u, or x du upon dx is equal to, here taking 1 plus u as LCM, we have 1 plus u square minus u, 1 plus u, or x du upon dx is equal to, here simplifying the numerator, we have 1 plus u square minus u square divided by 1 plus u. As it is obvious, u square positive and u square negative are cancelled with each other, and we have x du upon dx is equal to 1 minus u upon 1 plus u, which may also be written as minus, taking minus common out of these two terms, we may write it as u minus 1 upon u plus 1. Now transposing this expression, that is u minus 1 upon u plus 1 to left hand side and x dx to right hand side, we get u plus 1 upon u minus 1 du is equal to minus 1 upon x dx. Let it be equation number 4. As you see, equation number 4 is a variable separable form of a differential equation, so we may integrate both sides now. Now integrating both sides, integral u plus 1 upon u minus 1 du is equal to minus integral 1 over x dx. Integral u plus 1 in the numerator may be written as u minus 1 plus 2 on u minus 1 du is equal to minus integral 1 over x dx. If we split it up, so u minus 1 divided by u minus 1 becomes 1 plus 2 upon u minus 1 du is equal to minus integral 1 upon x dx. So integral of 1 with respect to u is u plus, and integral of 2 upon u minus 1 will be 2 log u minus 1, that is equal to minus log mod x plus c. Now transposing minus log x to left hand side, we have u plus 2 log mod u minus 1 plus log mod x is equal to c. This may be written as u plus log u minus 1 whole square, because using logarithmic property, this coefficient 2 can be taken to the power of the mantissa, plus log mod x is equal to c. Let it be equation number 5. Now since from equation number 2, y is equal to ux, so it implies that u is equal to y upon x. Now substituting u is equal to y upon x in equation number 5, we get y upon x, as the first term is u, plus log u minus 1 is there, so y upon x minus 1 whole square plus log x is equal to c. So y upon x plus log, if we take LCM inside the bracket, we have y minus x upon x whole square plus log x is equal to c, or y upon x plus, using logarithmic property, log m plus log n is equal to log m into n. We may combine these two terms as log y minus x upon x whole square into x is equal to c, or y upon x plus log. As you see, y minus x upon x whole square may be written as y minus x whole square upon x square into x is equal to c. This x will cancel one power from this. So we have y upon x plus log y minus x whole square upon x is equal to c. Now proceeding from this step, y upon x plus log y minus x whole square upon x is equal to c. Now transposing y upon x to right hand side, we get log y minus x whole square upon x is equal to c minus y upon x. As we know that if base of the log is not written, that is considered to be e. So here the base of logarithm is e, and using the concept implies that b raised to the power c is equal to a. That is, b raised to the power c is equal to a, or a is equal to b raised to the power c. So using this concept, we may write this as y minus x whole square upon x is equal to e raised to the power, this expression, e raised to the power c minus y upon x, or y minus x whole square upon x is equal to, we may split this expression up in e raised to the power c into e raised to the power minus y upon x, e raised to the power minus y upon x. And as this is constant term, we may replace it by some other arbitrary constant like c dash or b or a, whatever. So y minus x whole square upon x is equal to c dash e raised to the power minus y upon x. Transposing x to this side, we may write y minus x whole square is equal to c dash x e raised to the power minus y upon x. And that's your required solution of the given differential equation. Question number 2 is y dash is equal to x plus y upon x, and as you know, y dash means dy upon dx. So dy upon dx is equal to x plus y upon x. Since the degree of numerator is equal to degree of denominator, so it is a homogeneous differential equation. So let it be equation number 1, and then we have to assume y is equal to ux. Let it be equation number 2. Differentiating with respect to x, we get dy upon dx is equal to u plus x du upon dx. Applying product rule, we have differentiated u and x, and so first function as it is, and the derivative of the second function 1 plus x as it is, and derivative of first function, that is du upon dx. Now we have to replace dy upon dx by the expression u plus x du upon dx in equation number 1. So we have u plus x du upon dx on the left hand side, and on the right hand side the expression is x plus y upon x. Here x as it is, and in place of y we have to write down ux using equation number 2. So ux upon x. Now u plus x du upon dx as it is, and in the numerator we may take x common out of these two terms, so we get 1 plus u inside and upon x. Now this x is cancelled by this x. Now proceeding from this step, u plus x du upon dx is equal to 1 plus u. Now transposing this u to right hand side, we get x du upon dx on the left hand side, and on the right hand side we have 1 plus u minus u. So this u is cancelled by this u, positive and negative, and we have x du upon dx is equal to 1. Now transposing x and dx to right hand side, we have du is equal to 1 upon x dx. Now quite clear, it is variable separable form, so integrating both sides. 1 over x dx on the right hand side. Integral of 1 with respect to u is u, and on the right hand side the integral of 1 over x is log x plus c. Now finally, using equation number 2, from equation number 2 we have y is equal to ux. So u is equal to y upon x. So u is replaced by y upon x using equation number 2. So we get y upon x is equal to log x plus c. Transposing this x to right hand side, it will multiply both the terms. And finally we have y is equal to x log x plus cx. This is the required solution of the differential equation. Question number 3, x minus y dy minus bracket x plus y dx is equal to 0. So since the degree of every term is equal, so clearly this is a homogeneous differential equation. So if we identify an equation as homogeneous differential equation, we have to find the value of dy upon dx in terms of x and y. So in order to do so, we have to transpose this term to right hand side. So we have x minus y dy on the left hand side, and on the right hand side this term becomes positive. So x plus y dx. Transposing dx to left hand side and x minus y to right hand side, we have dy upon dx is equal to x plus y upon x minus y. Let it be equation number 1. Let y is equal to ux. Let it be equation number 2. Differentiating with respect to x, we get dy upon dx, and differentiating ux by product rule, we have u plus x du upon dx. Let it be equation number 3. Now from equation number 1, 2 and 3. Now we have to replace dy upon dx in equation number 1 by u plus x du upon dx with the help of equation number 3. So we have u plus x du upon dx is equal to, and on the right hand side x plus y is there in the numerator, so we write x plus, in place of y we have to write down ux divided by x minus ux is equal to, taking x common out of these two terms, we have x 1 plus u divided by, taking x common out of these two in denominator, we have x 1 minus u. Now x is cancelled by x and we get u plus x du upon dx, and on the right hand side we have 1 plus u upon 1 minus u. Now proceeding from this step, now transposing u to right hand side, we get x du upon dx on the left hand side, and on the right hand side we have 1 plus u upon 1 minus u minus u. Simplifying right hand side, we have to take 1 minus u as LCM. So in the numerator we have 1 plus u minus u 1 minus u. Now 1 plus u, if we open up this bracket, we have minus u plus u square divided by 1 minus u. Clearly this u is positive and this u is negative, so these are cancelled with each other, and we are left with 1 plus u square upon 1 minus u. It is better to take minus common out of these two terms in the denominator. We may write it as minus 1 plus u square upon u minus 1. Because if we take minus common out of these two terms, which is written over here, so the signs of these two terms are changed. U becomes positive and 1 becomes negative. So we may write it as u minus 1. Now finally, transposing this expression to left hand side and x dx to right hand side, we get u minus 1 upon 1 plus u square du is equal to minus 1 upon x dx. Now integrating both sides, we get integral u minus 1 upon 1 plus u square du is equal to minus integral 1 upon x dx. Now proceeding from this step, we may split this expression into two expressions as u upon 1 plus u square minus 1 upon 1 plus u square du is equal to minus integral 1 over x dx. Now opening the bracket, we get integral u upon 1 plus u square du minus integral 1 upon 1 plus u square du is equal to minus integral 1 over x dx. Now transposing this term to left hand side and this term to right hand side, and it is not mandatory to transpose these two terms on opposite side, but it is better because if we transpose this term to right hand side, it becomes positive, and this term on transposition to left hand side becomes positive. So u upon 1 plus u square du, and this term becomes positive on transposition, integral 1 over x dx is equal to, this term also becomes positive, so integral 1 over 1 plus u square du, because we have transposed this term to right hand side. Now here if we substitute 1 plus u square as y and we differentiate both sides, we get 2u du is equal to dy. Transposing 2 to right hand side, we get u du is equal to half dy. Be careful, this substitution is made only in this integrand. So we have integral 1 upon y into half dy, because here we have written y and u du becomes half dy. So we get 1 upon y into half dy plus integral 1 upon x dx as it is equal to integral 1 upon 1 plus u square du as it is. Now taking this half as constant coefficient out, the integral of 1 over y with respect to y becomes log y, and plus integral of 1 over x is log x, and on the right hand side integral of 1 upon 1 plus u square with respect to u is tan inverse u. Now putting back the value of y in terms of u again from this substitution, we get 1 upon 2 log 1 plus u square and plus log x as it is plus c is equal to tan inverse u. Now from equation number 2, we have y is equal to ux. So from this, if we find the value of u, that will be equal to y upon x. Now putting back u is equal to y upon x in this expression, we have 1 upon 2 log bracket 1 plus y square upon x square plus, we may write log x as half into 2 log x plus c is equal to tan inverse, and as u is equal to y upon x, so it becomes tan inverse y upon x. So now half log, we take LCM here in this bracket, x square is the LCM, and in the numerator we have x square plus y square plus half, and here we may take this 2 in the power of x using logarithmic property, so we may write it as log x square plus c is equal to tan inverse y upon x. So taking half common out of these two terms, inside the bracket we get log x square plus y square upon x square plus log x square bracket closed plus c, that is equal to tan inverse y upon x. Now half inside the bracket. Here is the situation of log m plus log n. So using logarithmic property, we may write it as log m into n. So log x square plus y square upon x square into x square bracket close plus c is equal to tan inverse y upon x as it is. Now this x square is cancelled by this x square, and now proceeding from this step, we get half log, and only x square plus y square is left, plus c is equal to tan inverse y upon x as it is. So finally we may write the solution as tan inverse y upon x. So finally we may write the solution as tan inverse y upon x is equal to half log x square plus y square plus c. So this is the required solution of given differential equation. Now question number 4 is x square minus y square dx plus 2xy dy is equal to 0. So observing equal degree of every term, we identify that this is a homogeneous differential equation. And when we identify this equation as homogeneous differential equation, we need to find out the value of dy upon dx in terms of x and y first. So we have to transpose this term to right hand side, leaving this term on the left. We get 2xy dy is equal to minus x square minus y square dx. Now transposing dx to this side and 2xy to right hand side, we have dy upon dx is equal to minus x square minus y square divided by 2xy. Let it be equation number 1. Now let y is equal to ux. Let it be equation number 2. Differentiating this equation with respect to x, we get on the left hand side dy upon dx, and on the right hand side using product rule we may differentiate ux as first function as it is, differential of second function 1 plus second function as it is, differential of first function as du upon dx. Let it be equation number 3. Now from equation 1, 2, 3, we may replace dy upon dx by the expression u plus x du upon dx. So on the left hand side of this equation we have u plus x du upon dx is equal to minus, and here in this expression x square as it is, and if we replace y by ux by equation number 2, we have u square x square over here minus u square x square divided by 2x as it is and y as ux, so ux. Now minus x squared should be taken out common, and 1 minus u square within the bracket upon 2x into ux becomes 2x square u. Now this x square is cancelled by this x square, and we have minus 1 minus u square upon 2u. Taking minus common out of these two terms, this minus becomes plus, so we may write it as u square minus 1 upon 2u. Now transposing u from left hand side to right hand side, so we have x du upon dx on the left, and on the right we have u square minus 1 upon 2u minus u. Transposing this term to right hand side, it becomes minus u. Now taking 2u as LCM, and in the numerator we have u square minus 1 minus 2u square. 1u square is positive and 2u square are negative, so ultimately we have minus 1u square and minus 1 as it is upon 2u. Taking minus common out of these two terms, we have minus u square plus 1 upon 2u. Now transposing u square plus 1 upon 2u to left hand side and x dx to right hand side, we have 2u becomes numerator and u square plus 1 becomes denominator. Du is equal to minus x dx, x upon dx on transposition becomes 1 over x dx. Now proceeding from this step, clearly this is variable separable form, so integrating both sides of this equation, we have integral 2u upon 1 plus u square du is equal to minus integral 1 over x dx. Now let 1 plus u square as alpha, it implies that differentiating both sides with respect to alpha, differential of 1 as 0 and differential of 2u differential of u square 2u du upon d alpha is equal to differential of alpha with respect to alpha is 1. Transposing d alpha to right hand side, we have 2u du is equal to d alpha. Now replacing 1 plus u square by alpha, we get 2u du as d alpha. So our left hand side becomes 1 over alpha d alpha is equal to minus integral 1 over x dx. Integral of 1 over alpha with respect to alpha is log alpha, because differential of 1 upon x with respect to x is log x, is equal to minus integral of 1 over x with respect to x is log x, plus constant of integration should also be taken in the same form, that is log c. Now transposing this term to left hand side, it becomes log alpha plus log x is equal to log c. Now log m plus log n is equal to log m into n. So using that property, we may write these two terms as log alpha into x is equal to log c. Now we may eliminate log on both sides. Simply we have alpha x is equal to c. So let it be equation number 4. Let it be equation number 4. Now replacing alpha by 1 plus u square again from this substitution, we have 1 plus u square x is equal to c. Now since from equation number 2 y is equal to ux, so it implies that u is equal to y upon x. So replacing u by y upon x in this equation, we have 1 plus y square upon x square 2x is equal to c. Taking LCM x square over here, we have inside the bracket x square plus y square upon x square into x is equal to c. So this x will cancel one power from here, and this x, only x is left in the denominator. This x should be transposed to right hand side, and we get x square plus y square is equal to cx. And this is the required solution of the given differential equation. Now question number 5 is x square dy upon dx is equal to x square minus 2y square plus xy. So simply transposing x square to right hand side, we have dy upon dx is equal to x square minus 2y square plus xy upon x square. Let it be equation number 1. Now let y is equal to ux. Let it be equation number 2. Differentiating equation 2 with respect to x, we get dy upon dx is equal to u plus x du upon dx. Let it be equation number 3. From equation number 2 and 3, replacing dy upon dx by u plus x du upon dx and y by ux in equation number 1, we get u plus x du upon dx is equal to x square as it is minus 2y square is written as ux whole square, so u square x square, and if we put y is equal to ux over here in the third term, it becomes ux square plus ux square divided by x square. So we have u plus x du upon dx is equal to, taking x square common out of all these three terms in the numerator, we have x square. Inside the bracket we have 1 minus 2u square plus u divided by x square. X square is cancelled by x square. Now transposing u to right hand side, on the left hand side we get x du upon dx, and on the right hand side 1 minus 2u square plus u was already there, and we have transposed this u to right hand side, it becomes minus u. So plus u and minus u are cancelled with each other. Now only 1 minus 2u square is left on the right hand side. Now transposing, now taking minus common out of it, we may write it as minus 2u square minus 1. Now transposing this to left hand side and x dx to right hand side, we have 1 upon 2u square minus 1 du is equal to minus 1 upon x dx. It is variable separable form of differential equation, so integrating both sides. So proceeding from this step, integral 1 upon 2u square minus 1 du is equal to minus integral 1 over x dx. Now, we may write 1 upon, this term may be written as under root 2 u whole square minus 1 square du is equal to minus integral 1 over x dx as it is. Now, since integral 1 over x square minus a square dx is equal to 1 upon 2a log mod x minus a upon x plus a. Using this identity, we may integrate this term as 1 upon 2, and because the coefficient of u is under root 2, so by change of scale property of integration, we must divide integral by under root 2, so we get 1 upon 2 under root 2 outside and log mod under root 2 u minus 1 upon under root 2u plus 1 is equal to minus integral 1 over x dx is log x. Now constant of integration should also be taken in terms of log plus c as constant of integration. Now from equation 2, as we know well, y is equal to ux. So if we find the value of u in terms of x and y from this equation, we have u is equal to y upon x. So replacing u by y upon x, in this equation we have 1 upon 2 under root 2 log mod under root 2 y upon x minus 1 upon under root 2 y upon x plus 1 modulus is equal to minus log modulus x plus c. This constant of integration may be taken as minus c or plus c, it doesn't matter, because we may take constant of integration from to left hand side and right hand side both. So suppose if we take this c on the left hand side, there will be plus c on the left hand side, and transposing this to right hand side we get minus c. So there is no mistake if you have plus c or minus c. So sign of constant of integration doesn't matter. 1 upon 2 under root 2 log. If we take LCM over here in numerator and also in denominator, so LCM will be cancelled by LCM, and we get in the numerator under root 2y minus x upon under root 2y plus 1 is equal to minus log mod x minus c. If we multiply both sides of this equation by minus 1, we get minus 1 upon 2 under root 2 log under root 2y minus x upon under root 2y plus over there x plus x is equal to log mod x plus c. And by the property of logarithm, if a log is multiplied by minus 1, and we eliminate this negative sign by taking the reciprocal of the mantissa. So if we eliminate this minus, we should interchange numerator and denominator. Over here we have 1 over 2 under root 2 log mod 2 under root y plus x upon under root 2y minus x is equal to log mod x plus c. So this is the required solution of the given differential equation, though you may leave your answer over here, keeping this minus 1 upon 2 under root 2 log under root 2y minus x here in the numerator and under root 2y plus x in the denominator. It doesn't make any difference.